Have you ever tried to open a heavy wooden door by shoving exactly here, right next to the hinges? You can push with all your strength and it barely budges. That metal pivot point absorbs almost all your effort. It completely resists the linear force you are applying. But move your hand just a few feet to the outer edge, give it a light tap with 2 fingers, and it swings wide open. In standard straight-line physics, a specific amount of force yields a specific amount of movement. But on this door, applying the exact same force yields 2 entirely different results. The only thing that changed was the location of the push. To understand rotational motion, we need a measurement that combines how hard you push with exactly where you push. Physicists call this the moment of force, or torque. This turning effect dictates how things spin. Measuring force alone simply does not give us enough information to predict how an object will rotate. Look at this 3D coordinate system. We place the door's hinge right at the center, marking it as our origin, O. The distance from that hinge to where your hand touches the door is the position vector, R. Now add your push. We draw a second line, the force vector, F, starting right at the tip of R. The relationship between these lines gives us the equation for torque, tau equals R cross F. This is a vector cross product. It takes 2 vectors and generates a completely new third vector sitting exactly at a right angle to both. To find out where this new torque vector points, you use the right hand rule. Curl the fingers of your right hand from the position vector R toward the force vector F. Your thumb now points straight up along the axis of rotation. Because this is a vector product, the order and direction matter. If you pull the door instead of pushing it, your force vector reverses. Your thumb points down, and the direction of the turning effect flips. Torque does not push the door forward. It builds an invisible mathematical axis perpendicular to your hand, forcing the object to pivot around it. Look at this flat, top-down view of the same system. We clearly see the angle between the door and your push, called theta. The magnitude of your torque is calculated as R times F times the sine of theta. To see how theta changes leverage, we draw a line of action, an infinite path extending along your force vector. The shortest line from the origin to this path meets at a perfect 90-degree angle. We call this the perpendicular distance. Alternatively, you can look at the force itself. Only the portion of your push that is perfectly perpendicular to the door actually contributes to the rotation. When your line of action passes straight through the hinges, the perpendicular distance becomes 0. No matter how hard you push, the torque is 0. Pushing directly into the edge of a door does nothing. Getting a door to move is an exercise in geometry. The closer your push is to a perfect 90-degree angle at the furthest point from the hinge, the more mechanical advantage you extract. This geometry dictates almost everything that spins. When a potter shapes clay on a wheel, they apply force at specific distances from the center, using torque to mold the spinning mass. When you pull a string wrapped around a top, you apply a force perfectly tangential to the outer edge, maximizing the initial torque needed to keep it upright. 2 children on a seesaw can balance perfectly, even if they are entirely different weights. By adjusting their distance from the fulcrum until their opposing torques cancel each other out, they achieve rotational equilibrium. The motor inside a ceiling fan applies a continuous torque to the blades. This overcomes the constant friction of the air, allowing the fan to easily maintain a perfectly steady angular speed. On a Ferris wheel, drive tires push against the extreme outer rim. This generates massive rotational force with relatively small motors, a feat that would be nearly impossible if they tried to turn the central axle directly. Even the Earth's magnetic field applies torque. It pulls the north pole of a compass needle one way and the south pole the other. These equal and opposite forces create a couple, which is a pair of forces that produce rotation without pushing the object across the table. Our mechanical world is an intricate network of pivots, hinges, and levers. All of them are governed by the exact same rule of perpendicular distance and applied force. You don't just need